So now I want to discuss continuous maps between topological spaces. So suppose we've got two topological spaces, x and y, and f is going to be a function from x to y. And so f is continuous, we say, if for every open subset so in the pre-image f inverse of v, which is, remember, the set of those x and x, for which f of x lies in v, is open in x. So remember, topological space, that's a set equipped with a topology. A topology is a collection of subsets that are known as open subsets, subject to some axioms. So yeah, so we've got, we can consider open subsets v and y, and then for each set, each subset v, we can consider its pre-image. Remember, that's the set of those points in x whose image lies in v, and that's got to be an open subset x. And so suppose x and y are metric spaces, and we give them the metric topologies. So remember, there's a definition of what we mean by open subsets in a metric space, and we showed that if you use that definition of open sets, then that gives rise to a topology. So we can use the metrics to regard x and y as metric space, as topological spaces. So the claim is the above definition is equivalent to the epsilon delta definition of continuity for maps between metric spaces. So this equivalence was a theorem in the metric space course, and we recorded that as proposition 3.12. So in principle we have two different definitions of continuity, but it's a theorem that they are actually equivalent. Okay, so as examples, we'll take for granted continuity results from real analysis. So for example, sine, cos, tan, sine, let's say sine, cos, exponential, these are maps from the reals to the reals. These are going to be continuous maps, and so the tan function, that's going to be continuous in the usual place. So we have to consider the reals, and we remove things of the form n plus a half pi. It's a continuous function, polynomials are continuous, etc. Then one kind of very, very basic example, it's useful to see how it works out in this case, is actually, let's do this on a new piece of paper. So let's let x and y be any topological spaces. Let's say any non-empty topological spaces, just avoid some trivialities. And let's suppose that f from x to y is just a constant function. Well, it's kind of very natural to assume that that should be continuous. Let's just see how that works out in terms of our definitions. So it's constant, so that means there's a point b and y, with f of x equal b for all x. So let's consider an open set v and y. So what do we need? We need to show that the preimage is open in x. So what is this preimage? So if b is in v, okay, so if b lies in v, then f of x is always in v, because f of x is always equal to b and b is in v. So that means that x is always in f inverse v. So the preimage f inverse v is the whole space x. And first axiom for a topology is that the empty set and the whole space have to be open, so f inverse v is open. And if b is not in v, then for all x and x, have f of x not in v, therefore x is not in f inverse v. So that means that f inverse v is empty. Okay, so either way around, f inverse v is an open set. So that proves that constant maps are continuous. So certainly, if that didn't work out, then the definition would be wrong. Another little thing we want to add to this is a different characterization of continuous maps. So again, let f from x to y be a function between topological spaces. So then I want to claim that f is continuous if and only if we've got this condition in terms of closed sets instead of open sets. Okay, so the original definition of a continuous map between topological spaces, we say it's continuous if and only if the preimage of any open set is open, but here I'm claiming that's equivalent to say the preimage of any closed set is closed. And this is not very hard to prove. So let's firstly suppose that f is continuous, and let G be a closed set in Y, then that means that G complement, or Y with G removed, is open in Y. So remember, closed set in our general topological context, closed just means that the complement's open. So and open is the same as the complement being closed. Okay, so this is open. And f is continuous, so f inverse of G complement is open in X. But f inverse of G complement is the same thing as the complement of f inverse G. This is one of these basic things about preimages, very easy to check. We wrote it down a little while ago. So we're now seeing that F inverse of G complement is open, therefore F inverse of G is closed. Okay, so that's kind of one way around it. If F is continuous, then the preimage of any closed set is closed. Conversely, suppose that the preimage of every closed set is closed. So then we consider an open subset.